Hello, folks, and welcome to what is going to be a completely normal, in no way, shape, or form strange semester of Physics 111. I know we are doing things a little bit differently this time around. I am here in my virtual space, and you are either at home, maybe on campus, hiding away in a corner somewhere. Perhaps you're one of the students who are living in a dorm. Perhaps you were forced to stay off campus, or you're commuting in from a family or friend's house, or maybe you're mooching off Wi-Fi at a Starbucks because this is the world we live in now. Don't worry, I assure you, this is fine. We are going to do our best to get through this together. Now, with that said, I do want to take a little bit of time here at the beginning of our first lecture to go over, amongst other things, how this course is going to work. All of this information is available up on the syllabus, which can be found on the course Brightspace. I apologize that the course Brightspace is not super filled out yet. This has been an absolute mad dash scramble in order to, get things ready for the semester. And this semester, despite my assurances, is going to be a little bit different, which means I'm a little bit behind schedule. The first half of the lecture notes that I'm going to be using today are uploaded on Brightspace, so if you want to go check that out and follow along, you can go do so. One of the nice things about me being in this infinite void of nothing is that you can always just click that pause button right down there, and if I'm going too fast or you want to go back and clarify, you have complete control over the dynamics of this lecture. Now, with that said, I would like to talk a little bit here at the start of class about the syllabus. Now, I'm going to let you read through this in detail yourself. Many of you already have. I'm just going to go over the important points here. The first is that there are two sections of Physics 111. This course taught by myself, and another course scheduled from 12 to 12:50 taught by Dr. Tamaro. And my garage door was open. Surprise. You're not going to be able to see that at all. That's fine. Now, Dr. Tamaro and I are really working side by side to make this as inclusive a course as possible. So we're really sharing a lot of materials. Some of you out there right now are listening in from Dr. Tamaro's class. That's great. Some of you will also, from my course, be going to join Dr. Tamaro in his Zoom meeting later today. This is perfect. We want you to succeed, which means you have access to both of our lectures. You have access to the textbook. We'll be providing additional material over the course of the semester. So really just take advantage of whatever resources are there that will help you succeed in this course, which we all know is going to be difficult enough as it is. Physics is a difficult course, famously taught by people who are physicists, who, let's face it, aren't always the most eloquent communicators. They don't always have the same worldview that you do, and so that can make it a kind of challenging experience. So we are saturating you with resources to make sure you can get the learning experience that you deserve the most in this semester that is, in fact, so messed up. Change something, close some of these other tabs that you don't need. Okay, with that said about the syllabus, office hours. We're doing it all through Zoom. The form of how you go through and get into the Zoom meeting is a little bit different. Mine is very easy. You just go in, you click the link that I will be posting to Brightspace. That's my meeting room. That's where I will always be. You just log in, click the button, and you're good. Now, as for when my office hours are, they are going to generally be Monday, Wednesday, Friday, so right after this class for an hour. Today is an exception. I have a meeting right after this, so I can't have walk-in office hours today. But right after class, there will be an hour of time when you can just come into my Zoom meeting, no appointment needed, ask any questions you want to ask, and that's fine. Other than that, though, I have wide availability in the afternoon through Starfish every single day from 1 to 5. Those are by appointment only. Just go into Starfish, schedule an appointment. I need you to give me like an hour's heads up just so I can make sure I'm there at my computer. But other than that, you can schedule an appointment. And I strongly encourage you to do so. In fact, some of you already have. Now, the text we're using this semester is College Physics. It is an algebra-based physics text, and we are using the homework platform Sapling Learning. Now, I hate the fact that I have to charge you anything for the privilege of getting the textbook and doing your assignments, but it is the world we live in. To that end, we have aggressively bargain shop for the cheapest possible option. The cost to you for the whole semester is $40. If they ask you to pay something more than that for like a different version of the book, don't do it. You get an ebook, you get the online homework platform, 40 bucks, you have everything you need. Now, of course, if you want to get a physical copy of the text, you're welcome to do so, but it will not be available in the school store. You'll have to turn to a regular book store. We didn't want students having to go out and spend $150 on a textbook they'll use once. Okay, with that said, there are instructions in the syllabus for how to log into Sapling Learning. I encourage you to do so promptly. The general outline of the course is here. We're covering almost all of Physics 1, including some information on gravitation, oscillation, fluids, and thermodynamics. You'll do note that we skipped Chapter 9. It's not super relevant to the reason why many of you are here, which frankly is either because this is a degree requirement for your program or because you're, say, looking to go to med school, you want to take the MCATs or the VCATs or something like that, and you want to have physics so you can pass those relevant sections of the course. And we determined that these other ones are a little bit more important than Chapter 9. On the next page, there's just an about. This is just the general education things that this satisfies. Down here, though, is the information on lecture. If you're watching this, you are viewing one half of the possible lectures. The other possible lecture is Dr. Tamaro's lecture from 12 to 12:50 each day, Monday, Wednesday, Friday, to be held in Zoom. I posted instructions for how to log in there on the Brightspace. Now, as far as assignments in this class, we're going to have 5 unit exams. These exams are all weighted equally, and they are each worth about 15% of your grade. Yeah, something like that. Now, the exams will be 50 minutes long. They will be proctored using something like Zoom. More information to come about there. You will need to be on camera for the proctoring of the exam. You'll be able to have to show, the contents of your desk where you're working. I recognize that this might be uncomfortable for some folks, but it's the only way we can try to maintain some sense of integrity, since we can't actually have you in the classroom and we can't send you to the testing center. If you were worried about your ability to get video, note that even if you have a computer that doesn't have a webcam, you can log into Zoom using one of these. Congratulations, my garage door was closed. Hooray. You can log into the meeting using your smartphone or your tablet, and that can be your video source for the exam. We will be having 3 blocks to take your exams in on each exam day. 1 during this class time, 1 during Dr. Tamaro's class time, and 1 in the evening for people whose schedules really do not allow for synchronous activity. Priority for those evening sessions will be given to people with real legitimate, reasons for why they have to do it. For example, there are folks in this class who are, practicing nurses, and they are on call during the day. So they'll get first slot, and then if there is free room, it will open up to people who kind of want to take it in the evening. The exams will cover the same topics, but the problems will be different. So somebody who completes the exam in the morning will have a different exam from the folks at night. This is just to prevent cheating. The final is a 50-minute exam, and it is entirely optional, but the way it works is if you complete the final, it will replace the lowest score of any of your previous exams. So that's a way of making up for a poor exam earlier in the semester. You'll be turning in your work through Brightspace. You can use the convenient Pulse app. It's available both on iOS and Android to directly scan and upload your scanned work. You'll have to fit all of your work on the front and back of 1 sheet of paper. You'll also be allowed an equation sheet, and you can use that for a little extra room. Dr. Tamaro did this over the summer and in the spring, and it worked out pretty well. We'll see how it works for us. To get familiarity with how to do this, there is an assignment on Brightspace right now called the ID Upload Assignment. This is just an assignment for you to use that scanner, whether it's on your device, using the Pulse app, scanner at home, however you want to do it, and upload a very clear image of your student ID. This will be used to make sure that you are the person taking the exam when we proctor it in the thing. It's a lot easier to be nefarious in this course, and we're working hard to make sure that everybody has a fair and equitable environment. Homework is administered through the Sapling online system. The Chapter 1 homework is up to date. This is the first time we are using this system, so we are in the process of building all the assignments. We'll try to get them up at least a week or 2 ahead of time, so if you want to work ahead. The ID upload is worth 2% extra credit. It's a nice little way to get a little tiny bump, about a third of a letter grade up on your grade just by submitting your thing. But importantly, this ID upload assignment is not optional. You must upload it or you will not be able to take the first exam. Other than that, we have a nice detailed course schedule, including the sort of approximate lab schedule. More information will be sent to you from your TAs. There are no labs this week. Those will start, I believe, next week. You should get instructions from your TA either through email or via Brightspace soon about how exactly these are going to work. They're all going to be online. There will be some videos you'll need to watch. You'll have online meetings where the TAs will talk you through some of the stuff, and then you'll be doing online analysis. We want to make sure that you remain safe during this pandemic, and that means not forcing you to do in-person labs. Class schedule here with the approximate breakdown of chapters by week. We're going to stick to this pretty clear. Some of these might move around a little bit, but the exams are more or less set in stone. So take a look over this now and make sure you are available for the exams. You do have the one wiggle room where you can take the final to replace something earlier, but there will not be any makeups given. Like, you have the 3 exam blocks on the day of that exam, so if you're worried about your availability, now is the time to look into that. And that's the end of the syllabus. We will be jumping right into content for the rest of the day today. But if you have any questions or concerns about the syllabus, you can shoot me an email, or you can go on to too many tools, Starfish, and set up an appointment for a one-on-one meeting. And hey, set up a one-on-one meeting anyway. Even if it's just to meet, say hi, face to the name, so I know who you are, and so you're not just a formless denizen of the internet void or a name in a chat window. Speaking of which, you may have noticed that somewhere over here or wherever it is on your YouTube, there is a live chat. You are more than welcome to interact with the class by asking questions, trolling me, whatever you want to do. We're on the internet after all. We should have a little fun with it. But any questions that you have, you can go ahead and put in that chat. I will monitor it over the course of class, so I will be happy to answer them for those of you who are attending live. Okay. Whew. Today's going to run a little bit over probably, but I am going to do my best to respect your time. We are in a situation where you have some classes in person, some classes online. I'm going to try to maintain the 10 to 10:50 time block. Today might be the only exception because I did spend about 10 or 12 minutes going over the syllabus stuff, but I am going to try to be very respectful of your time. There is a question in the chat. Are the lectures recorded? Yes. Every single one of these lectures is recorded and archived. That link that got you here in the first place, it will always work. It will always point to this lecture. And nicely, after about a few hours, 5 to 10 hours after I'm done recording and YouTube has finished processing the video, things like closed captioning will be automatically available. So make sure that this is a little bit more inclusive for those of you who may benefit from that. Thank you for the congratulations about the garage door, Zoe. I appreciate that. All right, so today we are talking about Chapter 1, which is really just an introduction to physics. We're starting off relatively easy. We're going to talk a little bit about physics as a topic, what physicists do, what they study, how we think about physics. We're going to learn about problem-solving strategies because I know this is going to be a little different from the classes that you might be used to. And then we're going to do a little bit of the rudimentary mathy stuff to just kind of set a strong foundation. And that will be things like units, significant figures, scientific notation, and I know that we are not even in the same room, but I just heard 100 people groaning at the mention of sig figs. I apologize, but they actually do serve an important purpose. So another question in the chat, is the ID uploaded through Brightspace? Yes, there is an assignment in the Brightspace page up in the assignments section. So, in the same place you'd go to find announcements or course content, in the assignments area, there is an ID upload assignment, and that's where you're going to want to upload your ID. If you have the Pulse app on your phone, it makes it super easy both to scan and upload. Highly recommended. Also has the benefit of giving you push notifications every time I make one of those annoying announcements that will be coming in regularly throughout the semester. So, I don't know, if you want to avoid me blowing up your phone, maybe don't do that, but your mileage may vary. Okay, introduction to physics. We're going to start off with the real simple stuff. What is physics? Physics and physical laws. You know, one of the ways I like to think about physics, and this is described very well in your textbook, is that physics is really a language that we use to describe the natural world. It is a sort of complicated language, one that is built out of equal parts mathematical rules as well as conceptual rules. And learning this language is going to be a big challenge. It was for me, and I'm sure it will be for some of you as well. So I'd like to set the scene by talking about some of the various areas of physics, what parts of nature we study as physicists and what are going to be relevant to this class. Now, this is a little, I don't want to say it's outdated, but this is a simplistic summary. Physics is actually a very widely varied topic, in the same way that all of your individual disciplines are varied. But basically, you can break physics up into four major categories. There's particle physics. This is the study of how elementary constituents of matter interact with one another. Protons, neutrons, electrons, how they combine together to form atoms. You know, this is closely related to the study of chemistry. Now, if you've ever heard of big experiments like the Large Hadron Collider or Fermilab, particle physics experiments, this is the stuff that we're talking about. We're studying constituent components of matter and their interactions. Now, next is astrophysics. That's where I live. I am an astrophysicist, and astrophysics involves the study of the universe on scales of planets, stars, galaxies, and so on. This includes not only interesting questions about the origin and fate of the universe, but also the variety of astronomical objects that are out there. I, for example, study black holes and neutron stars as part of a gravitational wave collaboration. So I study all sorts of stuff way out there in the far-off reaches of space. Atomic, molecular, and optical physics, AMO for short, is a broad category that studies how the states of electrons and atoms and molecules change and interact with electromagnetic radiation. This too is related somewhat to chemistry. These two are fields of the very small. Astro is a field of the very big. After atomic, molecular, and optical physics, we have so-called condensed matter physics. This is the study of condensed phases of matter, primarily solids and liquids, although you can also say gases, but predominantly solids and liquids. And these are much more macro-scale objects, like how do bulk properties behave. Now, once you have the disciplines, physicists themselves generally either practice experiment or theory. This is, again, a kind of simplification. Experimentalists design and execute experiments which gather data. Theorists then develop and refine mathematical models to explain the results shown by that data. Now, this is actually a real gross simplification. We don't have just two of these anymore. We have computational physicists, we have observational physicists, we have experimental physicists, we have theoretical physicists, and not only that, but we even have cross-disciplinary fields, particularly relevant to this class, biological physics or medical physics. You might not know this actually, but URI has a pretty good medical physics program where we train future technicians that will go on to help operate and design and construct the sort of scanning devices that you might end up using in the hospital someday if you are destined to become a doctor or a veterinarian or a nurse or anything like that. And historically, physics has been a give and take between experiment and theory. Sometimes physics is led by experimental results, where somebody observes something unexplained and theory adapts to try to explain it. Sometimes physics has been led by theory that give you predictions about how the world works, and experiments have been used to confirm those predictions. At its core, physics is its best when these two are giving and taking to and from each other. Now, physics is hard. Just straight up, it's tough. I have no doubt in my mind that many of you are dreading this course in Physics 111. This is often seen as a roadblock that stands in the way of bright young scientists like yourself going on to, say, medical school or whatever else. But it doesn't have to be that way. Something to keep in mind is that physics is a challenging subject, not just for, you folks. It's challenging for physicists, too. It's hard, straight up. But there's a joy to be found in challenge. There is a great sense of purpose to be found in deconstructing problems that are difficult and challenging ourselves to become better at doing things that we ourselves are not naturally gifted at. And to be clear, nobody is naturally gifted at physics, not even the real true greats. They got there through hard work just like everybody else. Some of the reasons that physics is hard is because it's a lot more abstract than other scientific disciplines. Less so in this course, but very much in Physics 112. There are just concepts that you can't get a gut intuition for because they describe things that you don't have a fixed point of reference. It's easy to understand that if I hold up a rock and I drop it, it falls down because you can do that experiment. It's easy to know that if you are driving in a car and you turn, you feel a sort of effect of inertia because you've presumably driven in a car or on a bus or on a bike. Physicists and physics teachers also tend to approach problems in very different ways than you might, which means we have a sort of disconnect between how we describe things and how you intuitively understand things. And we're going to work to try to overcome that. And physics also depends a great deal on mathematics that can be complex at times. There's a good question in the chat. Is physics considered difficult because what we know is constantly expanding? And are there more that we are learning about it? Yes, that is part of the reason. This is true, of course, of every scientific discipline that is advancing. There's always new stuff to learn. But for this particular course, the answer to that question is also kind of no. This is an interesting sort of feature of physics, is that once physical law has been shown to be correct, meaning it correctly predicts some output or phenomenon, that law is never disproven. That law will always properly describe the phenomenon that it was designed for. Now, you will later on down the line realize that there are other phenomenon that this rule no longer applies to, but that doesn't invalidate the original discovery. In this course, we're going to be studying a lot of physics that was discovered and refined in the 17th, 18th, and 19th century, starting with people like Isaac Newton in the 1600s and culminating in the works of brilliant scientists and mathematicians like Gauss and Coulomb and Ampere and Faraday in the Victorian era. Ultimately, part of the issue with physics just does come down to the math. There is a lot of math involved, and it gets more and more conceptually challenging the higher up you get in the hierarchy. But I am here to help you. You are in this class, and I am at your disposal for getting over these humps. Now, learning physics is kind of like learning a foreign language. The common approach in physics classes that I have observed personally is that we treat physics as there's a huge set of problems over here, and there's a huge set of equations over here. And the process of physics is one of those like junior high matching games where I have to fit which equation to which concept, and I'm just always trying to do that. To be fair, that is helpful for brief visitations or brief flirtations with physics. But that's kind of like just memorizing a few key phrases when you're traveling abroad. Like, yeah, that might help you like locate your hotel or order a meal, but you will not become fluent in that language by just memorizing a few key phrases. Fluency comes from building a vocabulary of words, learning how to combine those words with grammar, and using that framework, even a small set of tools can express an enormous variety of ideas, just like I am doing right now verbally to you. Now, in physics, our words or our phrases are things like rules, equations, definitions, and concepts. Many of these things do ultimately just have to be things that you commit to memory. But the actual physics, like the real sort of crux of all of this, is actually the grammar, the physical laws, how these things combine together, and from those we can build an enormous variety of explanations using a very small subset of tools. Now, with that being said, there is no single recipe for success in any class, let alone a physics class. But there are some approaches that you may find helpful. First, exposing yourself to the topics as much as possible with as many different voices as possible. I'm going to explain something one way. Your book is going to explain it a different way. Dr. Tamaro is going to explain it a different way. Each one of us will offer a partial window into the so-called underlying truth of what we're trying to discuss. And if you expose yourself to those topics repeatedly with different viewpoints, you'll start to be able to develop a clearer picture of what we're really talking about. Now, once you've done that, you'll want to study example problems to try to, get a feel for like, what's the basic process that I have to follow? What are the sort of algorithms I need to use? But beware, there are dangers in these waters, because you don't want to stick too closely to that. I'm sure many of you have had the experience of, say, watching a YouTube video or reading a set of printed up solutions to a problem, and then you get to an exam and you have a problem on the exam and you're stumped. Seems completely different. You go back and you talk to the professor like, hey professor, this really caught me off guard. And the professor says something along the lines of, what are you talking about? This is just like the example problem that we did in class. But there were subtle differences, really small things that to the professor who's been doing this for 20 years, it's obvious that this is the same. But for the student who's seeing it the first time, it looks like it's completely different. This step will, if you stop here, that's the experience you're going to have in this class. The only way to really develop physics skills is by then solving different problems that use the same concepts, use the same equations, but the problems themselves are different. You do that enough, and you start to see that sort of underlying sameness that the professor is referring to. To this end, the book provides a sort of framework to help you try to learn the process of approaching problems like this. Every book has its own different version of this problem-solving framework, but in effect, it's the same 3 steps all the time. You set up the problem, you solve the problem, you reflect on the problem. SSR in this particular case. Now, when we say set up the problem, we mean something very specific. We mean read the problem and start asking yourself questions about that problem. What is the problem asking for? What quantities do I know? What quantities do I not know? What quantities am I looking for? What concepts do I need to use? What equations should I apply? This is the step where you start to do that matching game. But it's not just the matching. You're also asking yourself, like, okay, is this more related to this concept or this concept? Which, you're thinking about it and you're trying to build these connections. To this end, drawing a picture, hugely helpful. Labeling all quantities, hugely helpful. Looking for connections between them. Having the ability to visualize the problem and see visually in front of you what you have and what you don't have will help you build the intuition for approaching this stuff. This process can take a long time. If you have 15 minutes to finish an exam problem, this might take you 5, 7, 9, 10 minutes out of those 15. And that's fine, because the next step, which is to solve the problem. If you've done this part, then this generally just becomes an exercise in going through the math. Now, sometimes that's easier than others. Your algebra skills are going to be tested at times in this course. So if you're a little bit worried about your mathematical framework, I'd suggest heading over to Khan Academy, checking out some of the refresher courses on algebra. You can shoot me an email. I am happy to meet with you one-on-one to try to work through some of this stuff. Even if you are worried that, like, look, it's a stupid question, I don't want to seem silly or anything. No, never worry about that. Yes, I'm a physicist. Yes, I know a lot of physics and a lot of math, but guess what? There are a lot of things I don't know. Every single one of you in this class could school me completely and totally, make me look like a fool in your own respective views. That's because I haven't taken, for example, a biology class since high school. I have a functioning understanding of biology, and I read lots of, popular science journals, but you know more about that than I do. Don't feel bad that I know more about physics than you do. Use me as a resource here. That's why you're in this class. That's why you're paying tuition. So you have access to an expert. Never ever worry about seeming silly for not knowing something in this class, even if it's basic math. After you've solved the problem, an important but often overlooked part of the process is to reflect on the problem. Sit down, pause, and ask yourself, does the number I got make sense? Do the units that I got make sense? And so on. So that last part will help you sort of figure out if you've done the problem right or not. If you are solving for a distance and you get units of time, you'll know you did something wrong. If you are solving for the height of a human being and you get 500 meters, well, 500 meters is taller than Godzilla, so I'm pretty sure like that's the wrong number. Those simple questions can help you self-judge whether or not you've done you've done a problem correctly. Now, for the next 20 minutes or so, I want to spend a little bit of time going into our first really kind of numerical discussion. So we're going to kind of start getting quantitative here a little bit. And we're going to talk about units, dimensions, and how we convert between them, because this is a common issue in this class, that we do a lot of different stuff with a lot of different units. And, you know, in our day-to-day life, we're used to, well, I mean, I'm used to saying, you know, hey, Alejandro, what is the, you know, how many fluid ounces are 3.6 pints, things like that. Or how many milliliters is an ounce, yada, yada. Like, I'm used to outsourcing that part of my brain to Google or Alexa or Siri or whatever else. In this class, we're going to actually have to work with this stuff because we'll be doing them in exam situations. So it's important that we develop a strong foundation for how to work with measurements. Now, in this class, we're going to be using SI units. This is the International System of Units, and if you were confused why it's SI instead of IS, that it's because this is from the French phrase for the system of units. In this system of units, we use the meter to measure distance, the kilogram to measure mass, and the second to measure time. Each one of these units is defined in a certain way. The meter is defined as the distance like light travels in this small fraction of a second. The second is defined as the duration of a certain number of oscillations in a cesium atom. This is how we build atomic clocks. It is related, in fact, also to light. Interestingly, this table, which is from a different text, and the table in your textbook say that the kilogram is defined as the mass of a platinum iridium cylinder kept at the International Bureau of Weights and Measures. This is not true anymore. The kilogram actually has an interesting history. It was originally defined as the mass of a liter of water. Take a liter of water, that's a kilogram. Still a pretty good approximation. But it wasn't quite good enough because it was hard to measure out exactly what a liter was. So they cast a platinum iridium cylinder that would not change size or mass very much, and they set that aside in the International Bureau of Weights and Measures and say, this is the kilogram. Anybody who wants to measure a kilogram, just bring your weight, compare it to this, and then bring it home. That turned out to be problematic. So in fact, in 2019, just last year, they replaced the definition of the kilogram with one that is defined in terms of fundamental physical constants and the light-based definitions of mass of meters and seconds. This is not exactly relevant for this course, but it is important to note that this redefinition means that all of our SI units are now constructed out of unchanging physical quantities as opposed to physical objects that you have to compare to. Now, these are the base units. It turns out there are a lot of other types of units as well. Many of these are combinations of the base units. We call these derived units, and they are the sort of complex units that we're going to commonly be using in this class. For example, velocity, or speed, is distance over time, so its derived units are meters per second. Energy is a complicated unit. It's kilograms times meter squared divided by second squared. But energy, for example, is such a common value, such a common quantity, that we actually give this derived unit a special name. We call it the joule. And you'll see that there are several derived units. For frequency, it's the hertz. For force, it's the newton. For pressure, it's the Pascal, that we give special names to these derived combinations of units. And over the course of homework 1 and the rest of this chapter, you'll get plenty of opportunity to practice how these units interact with one another. Of course, the SI units is not the only system of units that we have. Most of the stuff we interact with here on the day-to-day in the United States use the imperial or US customary units. It's worth noting that there is a very subtle difference between the British standard units and the US standard units. They are very minute differences that cause all sorts of headaches. But for our purposes, the imperial, the units are, British units are fine. The length is measured in feet. Mass is measured in slugs. Time is measured in seconds. If you do lots of work in certain branches of chemistry or physics, you might run into so-called CGS units. CGS because they use centimeter, grams, and seconds, literally CGS. Different base systems of units just built their systems on different fundamental measurements, but SI is the one we're going to be dealing with in this class. Of course, a little bit more challenging is the fact that we span many different orders of magnitude. Orders of magnitude are just a rough way of saying factors of 10 in scale. And to that end, we are going to be using a lot of scientific notation with prefixes to quantify units. Now, the ones that you are probably most familiar with are millimeters, centimeters, and kilometers or kilometers as common measurements of distance. For example, if you look on a regular plain old ruler, you'll see, in addition to inches, centimeters and millimeters measured. Kilometers are akin to miles, and so on. But in this class, we're going to use a lot of different ones. We'll go as small as micro and nano, and those get different symbols, where centimeters is cm, millimeters is mm, micrometers will be mu, the Greek letter mu, m. Nanometers will be nm, and so on. If you go up in the other direction, you might also see mega or giga. For example, in astronomy, when we measure distances, we often use a unit of distance called the light year, which George Lucas famously mangled in the very first Star Wars movie. Light years and a closely related unit called the parsec are measures of astronomical distance, and you will often see kiloparsecs, megaparsecs, and gigaparsecs come up when you read scientific literature on astronomical phenomenon. Now, once we have these, these units of scale here, it's a useful exercise to encapsulate just how complicated physics can be by expanding and looking at the range of scales that physics covers. At its absolute largest, physics answers questions involving the scale of the universe. And this is a staggeringly large number. 900 trillion meters. In scientific notation, that's 9 times 10 to the 26 meters. That's a really big number. There's a question in the chat about what did George Lucas do. Famously, in the cantina scene at the beginning, when they're discussing the nature of the ship, he describes its speed in terms of parsecs. This has been wonderfully retconned after the fact, but parsecs are a unit of distance, not speed. It's self-consistent now if you're a nerd like I am. Surprise, your physics teacher's a nerd, folks. I hope that doesn't catch you off guard. But in the original, it was a bit of a sloppy mistake. So anyway, largest is the scale of the universe is 900 trillion meters. That's a big number. But on the smallest scale, elementary particles are about 1/millionth of a trillionth of a meter. So that's 10 to the minus 18. Huge difference between these two numbers. But, you know, if I'm being honest, that's probably not actually the smallest scale. Smallest scale is actually probably the so-called Planck scale, which is really just too small to describe in words. It's 10 to the minus 35 meters. If you combine this, you'll notice that depending on where you draw your lower end, physics spans a stunning range of 45 to 62 orders of magnitude. That is to say, factors of 10. Our laws, physical laws, have to describe everything in between these extremes, which is hard. Compare this to other macro scale sciences, for example, like biology. You might see small things being like molecules or atoms in biological structures. That might be on the order of a 10 to the minus 10, a so-called angstrom. And on the large end, it might be adult organisms, say maybe up to a few hundred meters in size, or maybe colonies of organisms that maybe span a few thousand kilometers or things like that. Even then, we're probably only talking about something like 11 or 12 orders of magnitude. That's a big difference, and that's part of the reason why physics is so hard. Now, to that, with that in mind, we need to differentiate a little bit between the idea of measuring quantities with units and what the sort of dimension of that quantity is. So for example, the height of a tree can be measured with meters or can be measured in feet, but the fundamental nature of a height is its length or its distance. The dimension of a quantity expresses its fundamental nature. The height of a tree is a type of length. The duration of a movie is a time. The amount of matter is something that has a mass. These dimensions, length, time, and mass, are different from the units used to measure those quantities. Here it would be meters, seconds, and kilograms. Now, interestingly, not only do we describe each dimension with units, we choose to use SI units, but we also use symbols to represent quantities and their associated units. And we have tons of quantities, tons of units, and not so many letters in the Latin alphabet. As a result, we get a lot of reused symbols that show up a lot. A good example of that is capital T. When it is italicized, meaning you see it's a little slanted here, when the symbol capital T is used with italics, it can represent a temperature, a period of time, or a tension in a stretched rope, amongst other things. When T is not italicized by contrast, it represents a unit of a magnetic field, something from Physics 112 called a Tesla. Don't worry about the details of that too much. As a result, the context of the symbols that we use is super important. Two core applications of this concept of dimension in this course is sometimes we'll refer to dimensions without referring to specific units. So instead of describing a speed as kilometers per hour, we'll describe a speed as distance divided by time or length divided by time. But importantly, it's this one down here that all equations that we use in this class have to be dimensionally consistent. What that means is when there's an equal sign, the quantities on the left-hand side of that equal sign have to have the same units as the quantities on the right-hand side of the equal sign. This gets us to a process that we call dimensional analysis. It's a process that we use to check equations for dimensional consistency. Now, not only can this be an extremely valuable way of checking our work, making sure that the units worked out in a problem that we just did, but we can also use it to learn things about quantities that we don't know much about. Here is an equation that I provide to you with no context. None. No idea what this is. All I will tell you is that this d represents a distance and this t represents a time. So let's see if we can use dimensional analysis to figure out what that a is and what it might represent. Now, the first thing I'm going to do when I do dimensional analysis is I'm going to replace my symbols with words. I'm just going to write out in parentheses what the dimension of that number is. So for example, d, I have been told, is a distance. 1/2 is just a number. So in fact, well, I'll come back to that. I don't know what a is. and I know that t is a time. Well, here's the thing. 1/2, that's just a number. That doesn't have units, so I'm not worried about it. It doesn't have dimension. What I am interested in is finding out what this is. So I'm going to treat these parentheses like algebraic quantities. And when I have algebraic quantities, I can divide both sides by time. That cancels these out here, which means that my units of this unknown variable a will be a distance over time squared. I know that distance might be measured in meters, time might be measured in seconds. So if I take this result, I come back to my table over here, and I just scan down the way here. I look for meters over second squared. I go, hey, wait a minute here. Meters per second squared, that unknown a is an acceleration. And I've used dimensional analysis to learn something about this unknown variable. Turns out this is a very advanced process. You can actually get a lot of information. Fun fact, when I was going to get my PhD in physics, the very first assignment in the very first class that I attended at the PhD level was a lesson on dimensional analysis. It said, use dimensional analysis, derive the form of these 4 equations only using dimensional analysis. And up to a constant of proportionality, it works quite often. Now, it does not give you the whole picture. Remember, there was a factor of 1/2 here that we ignored for dimensional analysis. Dimensional analysis cannot tell you about the presence of these numerical values, but it can give you the approximate form, and it will generally be proportional to the result, and it is a great way to test your work. Let's say if we can apply a physics problem here that we don't know. We don't know any physics yet. Let's see if we can do something with dimensional analysis. Here we have a nautical mile, which is a unit of length commonly used in boating, and is equal to 1852 meters. So right away, I'm going to say, oh, wait, they're trying to tell me something about in this problem. I know that 1 nautical mile is equal to 1852 meters. Similarly, I'm told that 1 knot is a speed equal to 1 nautical mile per hour. Oops. 1 nautical mile per 1 hour. Now, this wants us to know how far a boat can travel in 10.2 minutes. So I'm going to identify that I know I'm given a time. It's 10.2 minutes. And I know that its speed is 6.75 knots. And it asks me to find how far the boat can travel, a distance. Well, I know that speed, just from looking at my units right here, is a distance divided by a time. So I know that the dimensional analysis of a speed is distance over time. So even though I don't have any physical laws yet to tell me how to solve this problem, looking at that, it does seem that if I multiply my speed, which is distance over time, by my time, those times will cancel out and I will be left with a distance. So the basic idea would be to take my speed, 1 knot, and I'd multiply it by the time. And that should give me the distance that the boat travels. But right away, we'll note that the problem tells us one more thing. It asks us to express our answer in meters. Oh, well, what I have there, none of that seems to make sense. So we'll come back to that in a second, because what we need to talk about first is how do we convert between different units? And that is related to the process of unit conversion. When solving problems, we'll often have to convert a quantity from one set of units to another. For example, converting miles per hour to meters per second, converting pounds as a measure of mass to kilograms, and so on. Converting units require use of conversion factors. For example, 1 mile is 5280 feet. 1 year is 525,600 minutes, and so on. And then there are other types of relationships for other units. A kilocalorie, for example, which is a unit of energy. You know, the calories you see in the back of your food box, that's 4.18 joules. Conversion factors can be found in Appendix A of your text. And what you generally tend to do here is you take these relationships, for example, 1 mile being equal to 5280 feet. We actually rewrite that as a fraction. We divide 5280 by both sides, and we end up with this ratio of 1 mile to 5280 feet. Then, if I were to take this result and say multiply it by, I don't know, 3 feet, note that these units will cancel out algebraically. As a general rule, you take the unit to be converted, you multiply it by the desired unit over the unit to be converted. So if you start with feet in the numerator, you're going to want to divide by feet by putting it in the denominator in order to get miles, and vice versa. So with that in the back of our pocket, let's see if we can go here and do some unit conversions. I know that 1 knot is 1 nautical mile per hour. I know that in 10.2 minutes, that's nothing I can do there, but I can start to take conversion factors. I know that I need to convert minutes to hours to get those to cancel out. I know that 1 hour is 60 minutes. Note that that will allow my hours to cancel with hours, my minutes to cancel with minutes. And then I also know from over here that 1 nautical mile is 1852 meters. So I have nautical miles in the numerator. I put nautical miles in the denominator because I want those to cancel out. So now my nautical miles cancel with nautical miles. And so I just now evaluate this formula. So that is 10.2 times 1852 divided by 60. We'll be talking a little bit more about calculator etiquette next class, but this works out to a distance of 314.84 meters. There was a question in the chat on the test, will you be given conversion factors or should you be memorizing them? You will have access to a single-sided formula sheet that can include conversion factors. You will not need to memorize them. You'll notice that this class is actually pretty low on memorization. This is probably in contrast to many of your other science classes where you need to have a very large sort of vocabulary of information. You know, less so here. You're going to get a formula sheet on your exams. Okay, we are 5 minutes over because I did mention I was going to go over today, but I really desperately do want to get you out of here before the top of the hour. I have two Oh, that's a good question. That's actually an excellent, this is why I love having you here live in class with me. There was a question in chat, where does the 6.75 knots come in? And that was actually a mistake on my part. That should be right in here. Excellent catch. Because obviously the boat is not moving at 1 knot, it is moving at 6.75 knots. So this would be 6.75 knots, which is the same as a nautical mile per hour. So just make that little correction here. Good catch, and I apologize for that mistake. And so that actually is going to change the math just a little bit, but that's an easy fix. Just times 6.75. That is 2125.17. There we go. Thank you. Good. Now, like I was saying, we're running short on time. I will walk through very briefly this other example. Normally we won't have a large discussion of syllabus material, so we'd still have about 5 minutes left of class and I'd have time for this. This is another example of a unit conversion problem. The Seawise Giant, which is a famously large shipping vessel, a big super tanker, largest ever built. It's now been scrapped, but it had a length of 458 meters. Just to put this in scope, you could fit 5 football fields across this thing. That's a really big boat. In this case, we want to know the length of the Seawise Giant in the British unit of feet. The conversion factor is not given to us here, so we'd have to go into the appendix to find it. Turns out the conversion factor as it's given here is 1 foot is 30.48 centimeters. And we would then just go through the process of taking our 458 meters. Now, we don't know, we know that this is, we're trying to get to feet, but we only have centimeters. And you'll notice that as I've written this here, nothing actually cancels out. This is an example where I have to do subsequent applications of conversion factors. I need to know that 100 centimeters is equal to 1 meter. Now, this particular conversion factor you can actually get from the table of scientific notation here. A centi is 10 to the minus 2. So this means 1 centimeter is equal to 0.01 meters. And this is, I can just multiply both sides of that by 100 to get 100 centimeters is 1 meter. My guess is that it will be helpful to just kind of keep in the back of your mind like the very commonly used ones, kilometers, centimeters, millimeters. You'll use those enough that you'll probably end up with them memorized regardless. And then once you have that, you just plug in the numbers. And the important thing to take away here is that the units can be treated like algebraic quantities, which means they cancel each other out. Centimeters cancel with centimeters, meters cancel with meters, and I'll leave it up to you to plug that into your calculator. The last slide I want to mention today is a bit of a warning. Some unit conversions can be really complicated. This right here, this example where I'm converting a density, which is mass per volume. Problems like this are invariably where students start to lose points on the first exam, because it's easy to say like, oh, hey, I just did meters and centimeters. I know 100 centimeters is 1 meter. So if I want to convert this 2.700 grams per centimeter cubed, I will take my 100 centimeters per 1 meter, and I will be done. Great, good, I converted my centimeters. Except we didn't. There are 3 factors of centimeters here. It's centimeter cubed. There is only 1 here. So although this would cancel, it would only cancel with 1 of these factors. I would have to subsequently apply 2 more unit conversions in order to successfully cancel out all 3 factors of centimeters. Moreover, that's how I get my 3 units of meters in the denominator here. Of course, I'm also not quite done. I still need to get rid of my grams. And this is another thing where you'd have to come back to your scientific prefixes. Note that kilo is 10 to the 3. That means it's 1,000, which means there are 1,000 grams in 1 kilogram. These grams would cancel with these grams. I'd be left with kilograms, and then 1, 2, 3 units of meters. So this is 2.7 times 100 times 100 times 100, and then finally divided by 1,000. And this gives me a final result of 2,700 kilograms per meter cubed. Note that we had a lot of extra steps here. So again, I'm very sorry that I ran over a little bit today, folks. I will generally try to be very respectful of your time. Don't forget that if you do need to leave, that's fine. You can just pause the video and come back. I will be trapped in this internet abyss forever if you so desire. With that said, we're done for the day. We will finish up Chapter 1 on Friday. If there was any concepts that you were having difficulty with today, feel free to pop into Dr. Tamaro's lecture. That starts at noon. That's just about an hour. I do not have office hours this morning, but I am available by appointment in the afternoon if you'd like to touch base and meet with me. Otherwise, I'll be responding to emails all day and continuing to flesh out the course Bright Space. Other than that, I wish you the best of luck in what is going to be a very complicated and weird semester. Strongly encourage you to do your best to maintain social distancing if you are on campus. I know you folks go to college to have fun, and I very much want you to do that, but I also want the university to stay open, so please try to be responsible. That's nice. I like that. Please know that I am sympathetic. I know that physics sucks sometimes. I am here to help you. Please try to use me as a resource. And otherwise, folks, have a great day, and I will see you on Friday.